Hello, and welcome to your very first pre-calculus video. Yay, you made it! So this is for you Monday, September 14th. So you are watching this video the day before we go over the sum of the 1.1 material. We will be splitting 1.1 up into 2 separate days. Now, if you're looking at the blank notes right now and you're like, oh my goodness, 10 pages, Ms. Twain, why would you do this to us? You may notice that this text box right here, starting with domain and range, is actually not the first page of those notes. It's in fact the third page. We took the 10 pages, cut that in half, so we're only going to be covering 5 pages of the material, and then even within that, we split that up into 2 days, just to make sure that we were not going through anything too quickly, especially during this first week. So we are only going to be covering pages 3, 4, and 5, and even then, I'm going to leave some of these notes blank so that we can go over them tomorrow as a class. But let's get started. So you may notice that this section 1.1 does in fact say functions. We're going to be covering functions, but the first question is, what is a function? Now, I normally go through and do an activity on the very first day of class where I make you read my mind, and we do things with like magnets on a whiteboard. It's very fun, but we're going to cut to the chase. My question in my mind was, what is a function? And a function, let me get the right utensil, there we go. A function is an example where every input, usually an x value, has exactly one output. That's not how you, we're just going to turn that into a u. There we go. One output, usually a y. Now, taking a look at this can be interpreted in many different ways. If you're thinking of this graphically, you may have heard of the vertical line test, like where you hold your pencil up and down and run it across the graph. If it only touches the graph once, it means it is a function because it means it has exactly one output. When we come to equations, you're able to plug something in, get something out, as you normally would. So whenever we're talking specifically about functions, we need to say, well, these inputs and outputs, how many of them can I use? Can I use just all the numbers? Can I only use some of them? How would we know? And that's where we take a look into domain and range. Now, domain is our x values and range is our y values. Now, I know that's one of those things that some people mix up every once in a while just because you learn so much in math, but I always think of it alphabetically, so D and R alphabetically, X and Y alphabetically. So that's how I think of it. Domain is our X, range is our Y. We're really going to be spending time today talking about the domain. Range we'll get to eventually in a few days. I'm trying to think of our calendar right now. It's just sometime in a few days. Anyway, when we're talking about domain, we have things called domain restrictions, essentially saying we can't do things all the time. And those domain restrictions, we in fact have 2 of them. There are 2 possible domain restrictions on a function, and they are listed here. So first, anything being divisible by 0, you're not supposed to do that. If you plug that into your calculator, be it graphing or scientific, it gives you a domain error or input error or something like that. The second one is the square root or any even root of a negative number. 0 is fine, you could take the square root of 0, but a negative number, square root of a negative number, gets us to imaginary numbers. Now, we will vaguely talk about imaginary numbers this term, however, we will not be able to delve deep into them, so feel free to do some of that research on your own. So now that we know about domain restrictions, let's go about finding some domains. So if we see down here, I'm going to try to move this very carefully because I found it could tilt. We have just a few examples of different functions, and we need to find the domain of them. So if we take a look at question A, I go, okay, that's getting into our second category of a square root or an even root. I know I'm not supposed to have a negative number there, but having 0 or any positive number is going to be okay. So when I do that, change in my pen color, we're going to say that anything under the square root, we know it can't be negative, but it can be equal to 0. So this is anything greater than or equal to 0, and now we just solve. So I'm going to start by subtracting 7 on both sides. And then here we're going to divide both sides by -2. Now, just because it's been a summer slash spring slash, I'm not really sure how long it's been since you've had to deal with inequalities like this. Whenever we are multiplying or dividing by a negative number with inequalities, we have to flip this sign here. So we actually end up with x is less than or equal to 7/2. Now, we can't end this here. We actually are going to always be writing our domain in interval notation. Now, there are two notations we tend to use, interval notation and set notation. Set notation is with the inequalities and many other features. Interval notations, that's with the parentheses and brackets. So just as a quick reminder, we use brackets when we mean, oops, including or equal to, and then we use parentheses for not including. Or not equal. Now, something you cannot be equal to is, in fact, infinity. So whenever we're dealing with infinity or negative infinity, we will be using parentheses for that. So again, back to our first example, x is less than or equal to 7/2. I see I can be equal to 7/2, so that tells me that I'm going to have a bracket around that, but x can be as low as it wants to be. It can be -2, it can be -1,000,000. So we're going to write that as the domain, or we're just going to use d to signify domain. We're going to start all the way at -infinity, and again, you'll notice a parentheses around that because you can never be equal to infinity, because what about infinity plus 1? Or I guess in this case, it's -infinity minus 1. Anyway, we can go from negative infinity all the way up to 7/2. We can be equal to that, so we're going to put a bracket around it. I'm also really quickly going to fix that parenthesis. So there's our first example. Now, when we take a look at example C, I'm just going sideways. If we take a look at example C over here, yes, my pointer's a lightsaber. I figured out how to do that, very excited. I look at this and I go, okay, what restrictions does it have? Is there anywhere here where I'm dividing by 0? No, okay. Is there anywhere here where I have a square root or an even root? Well, I have an even power right there with a 2, but that's not an even root, meaning that there aren't any restrictions. So if there aren't any restrictions, I can literally just use all the numbers. In this case, from -infinity to +infinity. And again, because you can never be equal to infinity or -infinity, we'll be using parentheses. Now, some people may be asking, well, isn't that there like that weird R thing we can use? This right here, this does mean all real numbers. And this does mean the same thing as -infinity to +infinity. However, I'm going to ask that we not use that, simply because this notation here is part of set notation when talking about domain and range, and I'm only going to focus on interval notation. So I just wanted to show that because I know some people would be asking. But let's try our next example, B. So taking a look down here, n of t over m of t, pardon me, where we have the given functions of n and m. So let's write this out. Let's see. N of t over m of t is equal to t plus 2 over t squared minus 1. Okay, so here I can see this goes into our first category of division by 0. We're not supposed to divide anything by 0, so I know that denominator cannot be 0. So the way that I'm going to set that up is say that, hey, t squared minus 1, you're not supposed to be equal to 0. It can be greater than 0, it can be less than 0, just cannot be 0 itself. So I'm just going to keep solving. When I'm solving with something like this, I'm going to just solve like I normally would. So I'm going to add 1 to both sides. Now t squared cannot be equal to a +1. And then to get t by itself, I'm going to square root both sides. I'll do that in a different color. And say that t cannot be equal to, do not just say 1. I know the square root of 1 is 1, but the square root of 1 is also negative 1. So t cannot be equal to plus or minus 1. So in order to get around this, we can have all of the possible values that we can have, t, tx, whatever you choose. However, just not 1 or negative 1. So what we're going to do is start from the most left to the smallest, depending on if you're looking at a graph or not. So we're at negative infinity all the way up to negative 1. We cannot be equal to negative 1, meaning we're going to use a parenthesis. Or our values can be from negative 1 all the way up to positive 1. And again, we cannot be equal to positive 1, so we're going to use a parenthesis. But it can be anything around 1. So it can be 0.9999, it can be 1.0001. So we use these union symbols right here in between to say, hey, we're going to create a little break right there and go from 1 to infinity. So these symbols right here mean or. So what I'm saying is my t value can be in this interval, or in this one, or in this one. So that's kind of how I would read that. Now for example D, we're going to be going over that in class tomorrow, so feel free to skip that. Let's move on to the next page. On to page 2, or I guess technically for you, 4. Sorry that I didn't cut that out in the Canvas. I'm going to try to figure out how to do that later on. Anyway, taking a look at example A here, I see, okay, whenever we're taking the square or an even root of something, we cannot do that for a negative number. So we're going to say that all of this stuff, whoops, sorry, all this stuff underneath the radical or the square root symbol has to be greater than or equal to 0. Because again, taking the square root of 0, totally fine. I'm going to solve like normal. 3x is greater than or equal to positive 5, adding 5 to both sides. Divide both sides by 3. We get x is greater than or equal to 5/3. So when I write out that domain, we are going to have, we can be equal to 5/3. That's our smallest or lowest number. And then we can go as high as we want all the way up to infinity. And again, remember, you can never be equal to infinity, so we'll use a parentheses here. Now, for example C, this is very similar to example B from the last page. We have h of t over k of t, so let's get that set up. H of t over k of t is equal to the cube root of t minus 2 divided by 5t plus 40. Now I want you all to be really careful here because a lot of people are going to think, oh look, we have 2 restrictions. We in fact only have 1. If we take a look right here, this is a cube root and not an even root. That restriction on the domain only applies to even roots. So this, totally fine. The only restriction we have is the possibility of dividing by 0. So we have to figure out what t value would make us divide by 0 and say, let's not do that. So we're going to say, hey, 5t plus 40, you're not supposed to be 0. Subtract 40 on both sides. Divide both sides by 5. Whoop, there should be a negative right there. So t cannot be equal to negative 8. So it can be anything lower than negative 8, anything higher than negative 8, but not negative 8 itself. So to get around that, we're going to say the lowest number we can use is negative infinity. Go all the way up to negative 8, but we cannot be equal to negative 8. So we can go up to here, or our t value might be just bigger than negative 8, and all the way up to infinity. So we use that or symbol to kind of help us get around what x or t cannot be equal to. So we have examples like in example A where we only have 1 interval, example C where we have 2, but we can have more than that, and you might see where this is going. Let's take a look at example B. So for example B, I see a rational function, meaning a fraction, with polynomials top and bottom. I'm going to say let's factor. And it's probably been many moons since y'all have factored. So just a reminder, we're looking for numbers that multiply to the c value, and add to this b value. So just for my numerator, at the top of my fraction, I'm looking to see what numbers multiply to 10 and add to negative 7. So in our case, there we go. Come on, there we go. Those numbers that we can use are negative 5 and negative 2. Oops, sorry, that I just got an email. So it's x minus 5 and x minus 2 below, or pardon me, on top. And below, we are looking for two numbers that multiply to negative 6 and add to 1. And that is going to give us positive 3. And again, negative 2. So when I look at my restrictions here, I go, okay, again, I'm not allowed to divide by 0. I'm not allowed to divide by 0. So I'm going to take both of these factors right here, say, hey, neither of those can be equal to 0, and then solve. So I'm going to set this up into kind of two different equations. So we'll have x plus 3 cannot be equal to 0, and that's from that first factor. Subtract 3 on both sides. So I know x can't be negative 3. If I plug that in, that's bad. Or for my other factor, x minus 2, that also cannot be 0. Now, I'm aware that we have a factor of x minus 2 in the numerator and in the denominator, so they cancel out. But if we were into our original equation, plug in a 0, this would still be, or not 0, pardon me, 2. That would still be bad. So even though it does cancel, we have to consider the original equation. So here we have two numbers that x is not allowed to be. Cannot be negative 3, cannot be 2. So we're going from negative infinity to negative 3, or x can be anywhere between negative 3 and 2, or anywhere between 2 and infinity. So here's just a few different situations on restrictions of the domain. We're going to leave example D for class tomorrow. We got one more example to go through, and then we'll be done. I'm so sorry this video was so long. I think it was the long introduction. Last example. Oh, you can't see me, but I'm like waving my arms around. Once you get to know me a little more, you'll get to understand probably what gestures I'm doing in the background. Anyway, we are just going to start with function operations, meaning adding, subtracting, multiplying, and dividing various functions. Now, example 4 has two parts. It asks us to both add f of x and g of x and divide f of x and g of x. However, we're going to leave the dividing for tomorrow in class. Right now, we're just going to do the adding. So we're going to take these two functions, add them together, and then we are going to state the domain as well. So let's get cracking. So just a reminder, when it says f plus g of x, remember this is not times x, this is saying of the function. This is the same as f of x plus g of x. This is already written above. I will be using both notations just as we go through examples so that you can see them both. However, if you feel more comfortable with one function or with one type of function notation, feel free to just always change it to that if you want to. Just please make sure that you understand what both of these notations mean. Anyway, let's get to it. We know that f of x is a number, is x over x plus 3. Yes, I realize that it's just not a number. And g of x is 3 over x plus 3. So we have our two functions. Luckily for us, the thing you need to add fractions together is a common denominator, which we already have. So I'm going to add my numerators together, x plus 3. Keep my denominator the same. X plus 3 divided by x plus 3, anything divided by itself, 4 divided by 4, 8 divided by 8, x divided by x gives us 1. And that happens sometimes. So yay, we have found our f of x plus g of x, but now we need to find the domain. Now you may look at this and be like, well, the domain is 1, but we can't say that the domain is 1, our answer is 1, but we can plug anything in for x, except we see down here we are dividing by something. Now I know in our final answer it's just a number, it's a constant, so we're not actually technically dividing anything. We always have to go back to our original function. So I need to figure out, hey, what would I plug in here into my denominator that would be bad, that would be dividing by 0? And you may have already done that in your head, but let's just show a little bit of that work. So I'm saying, hey, this denominator here, that's not supposed to be 0. So I'm not supposed to plug in -3. And I can even write that as kind of a little notation at the end of my answer. But this is not enough. I still want us to practice writing our domain in interval notation. So we're going to say that the domain is from -infinity all the way up to -3, because we can plug in any of those numbers, or we can plug in -3 or anything larger than that all the way up to infinity. So I'm going to leave this here today. This video was, oh, I'm so sorry, just a little over 20 minutes. It's going to be shorter tomorrow, I promise. I look forward to seeing your faces. Enjoy the rest of your day.